Section 4.6. Perform operations with complex numbers. The complex number is useful for us because there are times when we're solving an equation, we end up with maybe a negative sign under a radical. And if that negative sign is under an even radical, so square root, fourth root, sixth root, eighth root, the complex number is going to be a solution for that particular problem. If I have a problem that gives me a negative number under an odd root, third, fifth, seventh, ninth root, I do not have a complex number that will result from that. And let's talk real quickly about maybe why that happens. So if we remember by definition, a square root of some number, I'm going to just use a simple one here, 4. The square root of 4 is asking you to find two identical numbers that multiply together to produce the 4. And you and I know that if I were taking a square root of 4, we could say that a negative 2 or a positive 2 multiplied together would produce a 4. Negative 2, or positive 2, positive 2. If we change that so that I end up with a square root of a negative 4, now I have a negative underneath the radical. My radicand is a negative 4. And I ask myself the same question. What are the two identical numbers that multiply together to produce a negative 4? I am stuck at this point because you and I both know that a negative results from a positive times a negative. And those are not identical numbers. And so in order for us to deal with this, we have this idea of a complex number, where that negative simply comes out as an I. We leave the 4 inside there. And now we can say, what's the square root of 4? 2. So this whole thing would become, we're talking about a principal root, that would just become now 2i. And where we see some complex numbers, we see it in circuit design as a commonplace. So we need to know how to manipulate them. And these are the two components that we're going to have to become familiar with, that the imaginary unit, I, is equal to the square root of a negative 1. If I chose to square both sides of that equation, I get an I squared on the left. And when you square a radical, remember we talked yesterday about how that just eliminates the radical and I have just the radicand. So that's why I squared is equal to a negative 1. We're going to use those two relationships right there to help us with the simplification or solving of problems that involve complex numbers. All right. So here's a little rundown on the square root of a negative number. Just talked about the idea of pulling out the I and being left with that R there. All right. Let's go work some examples. If I ended up with problem of 2x squared plus 18 equals negative 72, we're going to solve the quadratic. We know it's quadratic because it's power of 2. Solving it means we're trying to look for this value of x. And there is no x term here, so we're able to use the square root property, just isolate the x squared. And by doing that, we get 2x squared, and then subtract the 18 equals negative 90. And then x squared would equal negative 45. And then we take our square root. All right, we're taking the square roots. We're going to get our two answers here. The square root of negative 5, or negative 45, is the same thing as the square root of negative 1 times the square root of 45. Well, the square root of negative 1 is an I. So what this really becomes is I root 45. The 45, we can simplify. Remember we were doing this. Oh, that's a perfect square. And then those two are both prime. So the final answer here would be that x equals 3i square root of 5. So combining a little bit of simplifying radicals and then introducing this concept of the I. So the easiest thing to remember is a square root of a negative number. If that negative just pops out in front of the radical as an I, leave the number inside the radical and see if it can be simplified. Let's try it on this one. Again, isolating the x squared. X squared is equal to negative 25. Square root this thing. And there's the I that pops out. And that just simply goes to plus or minus 5i, because now the square root of 25 is our 5i. Complex numbers use the imaginary unit. They are made up of real parts and the imaginary part. And the constant a of a complex number is real. The coefficient b in front of the I is real. The a by itself makes up the real piece of the complex number, and the bi part makes up this imaginary component of the complex number. And this a plus bi is what we refer to as standard form. It can also be a minus bi. So when we write our solutions for these complex numbers, we're going to always want to create our answers into a complex form, or a standard form. If our b can't be equal to 0, so we're talking about right here. So if the real part of the I term can't be 0, then we have a plus bi as an imaginary number. If a happens to be 0, b cannot be 0, then we have just a bi situation, and that is known as a pure imaginary number. And over on the right-hand side, we see some relationships between the real numbers and the imaginary. If you take two complex numbers and you find that they are equal to each other, then that would mean the real parts a and c are the same. The coefficients b and d are the same. And so we can have a situation where, given some complex number x plus yi equaling 5 minus 3i, this would tell us that the x and the 5 are the same thing, and that the y and the 3 are the same thing. Sums and differences of complex numbers. So adding or subtracting complex numbers. All this is it's combining like terms. Where we have our real parts combining and our imaginary parts combining together. So in this example here, we have our two complex numbers, a plus bi, c plus di. Notice that the real pieces form the real part of the answer of this complex number. The imaginary form the imaginary component for that complex answer. So let's put this into some application. The thing you need to remember with our subtraction of two complex numbers is that this negative is going to distribute inside here. So just be careful with the negatives. All right. The reason we put parentheses around these numbers is to denote that they are complex, and that we're not simply just working with a variable expression that has an I in it. We're trying to confirm that that I is a part of a complex number. All right, we have our two complex numbers, 12 minus 11i. We're going to add that to negative 8 plus 3i. So again, think of combining like terms, real part, real part. This would become our a part of our standard form of a complex number. And then we have our imaginaries adding together. So we have a negative 11 plus a 3 now we just simplify that. So 12 minus 8, 4, negative 11 plus 3, negative 8i, and there I am in my standard form. Let's try B. We have 15 and the 24, creating our real piece. We have the negative 9i and the, and we got to remember we're going to distribute this negative here. So this is now plus 9i. And I get negative 9 plus 0i. The reason I'm writing the plus 0i there is because we're leaving our answer in standard form. However, negative 9 plus 0i is a real number. If we go back to the table that we looked at, here's an example of that. When your b becomes a 0, we actually just end up with a real number versus a complex number. And then C, we'd end up with 35 in our real components. 35 minus 13, remember to distribute. And our imaginary components are going to become a negative 4i plus an I. 22 minus 3i. So adding and subtracting, being careful of the subtraction. Then we get into the multiplication of complex numbers, and this is simply distributive property. Foiling, expanding, same thing. And these problems, often with complex numbers multiplying together, you have an I and an I, and we know, based on our look, I squared is equal to a negative 1. So we're going to keep that in mind as we're doing this multiplying complex number portion. All right, first one, we would distribute. We're distributing the imaginary piece to the real part and the imaginary piece to the imaginary part. So we have negative 5i times 8 and a negative 5i times negative 9i. Here's negative 40i's. Here we get 45i squared. Now, what you can do with every time you see an I squared is you can put a little line through it, make it a negative 1. Just to remind yourself that that's what's happening. And then you end up with negative 40i plus 45 times negative 1. And if we put ourselves in standard form, we'll put the real part out in front and the imaginary part later. And we get negative 45 minus 40i. For part B, we're going to end up distributing this via, you can use the FOIL method. So remember the FOIL method, the firsts, and the outsides, and the insides, and the lasts multiplied together. So we get that 8 times 4, and then we get an 8 times a negative 7i, and then we get a 2i times a 4, and then we get a 2i times a negative 7i. Now, I didn't put any plus minus in between those because we're going to get that from the products of these terms here. So there's my 32. This is a minus 56i, and that's a plus 8i, and this is a negative 14i squared. So once again, I will take my I squareds and make them negative 1. Combining my like terms, I would get 32 minus 44i minus 14 times negative 1. Which becomes positive 14. 14 and 32 is a 46, and then minus 44i. Another example. Again, as I'm doing these examples, again, remember, you want to try it, and then and check your answer, then pause the video right now, work out the problem, and then press play again and see what we end up with. See how you're doing. That's a great idea, is to always just not run through and watch this, but give yourself an opportunity to try some of these problems on your own and see what we get. So, on this one, kind of take some shortcut methods here. I'm just going to do it real quick. And showing, I don't have to do that. I'm just explaining how the process works. We're going to end up with a negative 10, and then we have a negative I, and then plus 2i squared. And I'm going to change that to my negative 1, making that negative 2. And we end up with this. In the chapter section 4.4, I believe, we talked about this idea of a conjugate, but it was in terms of radicals and how we use conjugates to help us rationalize denominators, getting rid of radicals in the denominators. Well, the job of the conjugate for a complex number is the same thing. Its job is to eliminate the I term from the denominator. And so, just like with the radical conjugates, when it was just the opposite of the second term, it's the same thing for a complex conjugate. So an A plus BI has a complex conjugate of an A minus BI. So we're going to try that on these problems here, utilizing the denominator's complex conjugate. We don't worry about the numerators, just the denominator. So looking at this problem, I have a 5 minus 9, which means its complex conjugate is 5 plus 9. And I'm going to always recommend put parentheses around these complex numbers. If you don't do that, then what you might have is a situation like this, where you go 3 plus 4i times 5 plus I. And you might forget that this 3 is a part of a complex number, and you mistakenly just multiply the 4i. Now you've left out the real part of that other complex number there, and obviously something's not going right there. So put parentheses around these complex numbers. They're stuck together. All right, we FOIL these out. On the top, we're going to get a 15. 3i minus or plus 20 is a 23i. And a 4i times an I is a 4i squared. The I squared becomes negative 1. And now I have a 15 minus a 4 plus a 23i on the top. On the bottom, I have a 5 times a 5, a 5 times an I, which is a 5i, a negative I times a 5, which is a negative 5i. So we should always get that middle term to cancel. And then a negative I times a positive I is a negative I squared. And once again, we make the I squared become negative 1. So now really I have 25 minus a negative 1, or 25 plus a 1 here, 26. And I'm going to write this as a complex number in standard form by leaving that 26 as a denominator under each of the two terms from the numerator. So I would want to write it as fraction plus another fraction. If I wrote it like this, we're just not in complex number standard form. So I want to be in standard form, so don't write it like that. Take that denominator and spread it out between the real part and the imaginary part of the complex number above. All right, let's try this one. Complex numbers of 2 minus I and 2 minus I. So we get 12 minus 6i plus 8i minus 4i squared. That becomes negative 1. All over 4 plus 1. So there's a trick here when I have my conjugates working together. Square the first one. Square the coefficient then you're always going to end up with an I squared, a negative I squared, so that's always going to become positive. So you can just simply square the first one, get a 4, and then plus the coefficient of the second. So 4 plus 1, you're giving me a 5. On the top, I have 12 plus 4, which is 16. 16 plus 2i over 5. Separated, 16 over 5. 2i over 5. Now we are in standard form. Like the Cartesian plane with our real numbers, which have coordinates of x and y, a complex number can also be plotted on its own plane, and that's the complex plane. The complex plane is made up of two axes, just like our Cartesian plane, and the x-axis is comparable to our real number, and the y-axis is our imaginary number. So we break these things up into imaginary versus real parts. Now, plotting the complex number is, you can think of it still as like plotting a coordinate. But what we're going to plot is we're going to plot the real, comma, imaginary. And that's going to be our point. We're going to plot the real and the imaginary. So looking at A. A is actually a complex number in which the real portion is a 4, or a 0, and the imaginary portion is the negative 4i. So all I'm doing is putting this in standard form. 0 minus 4i is the same thing as just 4i, negative 4. Thinking about how the coordinate would show up from this, the real part is the 0, and the imaginary part is that negative 4. We won't do the I. We'll just take the coefficient with the I as our imaginary piece. So a 0, negative 4 would be this first point. So we would be right there. That's 0, negative 4. 4 plus 2i. Think about the real and the imaginaries. Tell me to go on the real axis, right 4, and on the imaginary axis, up 2. So there's 4, 2. Negative 1 plus 3i, negative 1, 3. Go left on the real, and go up 3. And then on D, 2 in the real, negative 2 in the imaginary, and we end up right there. So that's plotting our complex numbers. The reason we're looking at the complex number plane is because it will help us develop the absolute value of complex numbers. Again, absolute value, go back to thinking about our definition of absolute value. Absolute value is referring to a distance from some number. Distance from 0 or distance from another number. And our absolute values are always positive. Such will be the case with our absolute values of complex numbers, except now we're not measuring our distance from a 0 like on a number line, but we're measuring our distance from the origin of the imaginary and the real plane. So we're measuring our distance of complex numbers from right there. And here you see we've got this coordinate out here. There's a complex number that's been plotted as a point. And that point has been created from a real piece and an imaginary piece. And we create this triangle. And we know that in a right triangle, if we wanted to find the length of the hypotenuse, we would simply use Pythagorean theorem. So there's my hypotenuse length. That's that distance that we want from our origin out to that point. And so we simply are saying that the absolute value of some number, we used in this textbook, we're using C to denote the absolute value. It's found by the square root of a squared plus b squared. And again, all that is it's derived from Pythagorean theorem. So if we do that, and we again identify the right parts, there's the A part, there's the B part, and we know that the absolute value of this number, which is the absolute value of 5 minus 12i, is equal to the square root of the real part squared plus the imaginary part squared. And that becomes the square root of 25 plus 144, which is the square root of 169, which is 13. And that's all there is to the absolute values of a complex number. It's just the real part squared plus the imaginary part squared. All right, we're going to do this one. This is a little weird. What am I missing? I don't have it. Oh yeah, it's really 0. The real part is the 0. Imaginary part is the 17. And we what? 2, is it 289? I think it's 289, square root of 289. Well, all we're doing is taking the square root of 17 squared. And then lastly, negative 3 plus I. Absolute value of that. Real part squared. Imaginary part squared. Square root of 10. Can't simplify it, so we're going to leave that answer alone. Hope that helps.